Thank you. Thank you very much, Yazoo, for the super generous introduction. Thank you very much. Also for having me here after many years. It's a great pleasure. And yeah, the topic for today is going to be some compressible structures for K-meters. There are substrings of length K, you probably know, and they arise in many contexts in bioinformatics. And I've decided to talk about this for a couple of reasons. The first reason is because this lays naturally the background for the talk I'm going to give at the workshop in 2 days. So this is kind of the basic data structure. And on July 4th, we'll see an application on top of this dictionary data structure. The second reason is, as you see from the agenda, it allows me to introduce you to some tools that are very important for computational biology, like spectrum preserving string sets, minimizers, and minimal perfect hashing. Of course, it will be very high level. Given the allotted time, we don't have to see all the details, of course, but my hope is that you'll find these tools interesting also for your own research and maybe outside computational biology. For sure, these tools can be used in many other contexts. So that's the agenda for today. Apart from some context, motivations, and problem definition, we'll see these tools. We'll sketch these tools, and then finally we're gonna put together all the three into a solution for our problem called SS hash. That stands for sparse and skew hashing of K-mers. All right, so again, just a little bit of context and motivation. So I'll be brief on this part since, I guess you all know what we are talking about here. So, of course, we have like a massive collections of DNA, many sequences. So we have these publicly available collections that host like petabytes of data, okay? And I have updated these statistics a few days ago. So we have like 30 trillion bases like available to index and search. So, so as computer scientists, really we want to answer this question. So how can we exploit this potential? No, because of course we would like to index and search, this data at that scale. And that's of course a problem, okay? And one popular strategy to be able to process this data is to reduce like such long sequences of DNA to a set of short substrings of fixed length K that are the so-called K-mers. For sure, you have already heard about K-mers since they're very popular in bioinformatics, so also outside bioinformatics, information retrieval, machine learning, and other contexts. But they found like profound use in bioinformatics. And here you have a simple example. So given a long string of DNA, we extract, as you can see, consecutive K-mers from the string. So this is an example for K equal 13. It's not very important. The K here. What's important is, of course, that, as you can see, consecutive K-mers share K-1 symbol overlaps. Okay, so that's an important feature of this kind of substrings. And that we're going to exploit, of course, in the following. So since K-mers are very popular, they have found like countless applications, and in fact, software tools based on K-mers are like everywhere in bioinformatics for genome assembly, variant calling, pangenome analysis. So I confess that I'm not an expert of these applications themselves. I consider myself a data structure guy. So, but I know that they are like used everywhere. And as a matter of fact, the community has produced a lot of indices based on K-mers. Okay. So I point you to these two excellent surveys on the topic from some years ago. Now, probably they should be integrated with some new development, but still there are excellent sources to know about these K-mer-based indexes. And since they are surveys, they cover like the more or less the entire spectrum of indices. So we have representations based on hashing, on BWT, and we have XSET, approximate methods. So we have a, so to speak, a little bit of everything. Different features like statics versus dynamic data structures. Some indices differ from others for the types of queries that they support, okay? But this is the problem that we deal with for this talk. So the fundamental problem that is common to all those indexes is the following one. So we're given a set of k-mers, okay, coming from a large string S or a large collection of strings. And let's suppose that K is the set of all these distinct k-mers. What we want is a dictionary for K, okay? So an XSET data structure that supports these two operations. So the lookup and access, which are the inverse of one another. So lookup, as you can see, takes as input a k-mer, X, and returns a unique handle, a unique identifier I between 1 and n, where n is the, of course, total number of k-mers stored in my dictionary. And if the k-mer X does not occur, so it does not appear in my dictionary, then I return a invalid identifier, okay? Something like a null identifier. And the access operation is exactly the inverse, okay? So I take as input, as you can see, the identifier of the k-mer, and I return the k-mer string, like all the characters in the k-mer. So I decided to shape this problem in this way with these two operations, lookup and access, because this mimics the original string dictionary problem that is very famous in the algorithmic community. But to be honest, it's the lookup operation that really matters for, at least for computational biology, applications and problems. I'm not actually aware of any use of access, although the data structure we're going to see at the end of this talk also support access. But from now on, I'm going to focus on lookup. So apart from lookup and access, there are also other important queries to be supported. Again, I will not talk much about those, but there are also streaming queries. So namely, a streaming query is when you issue lookup exactly in order, okay, for k-mers in order, so appearing in order in a string, in a query string, and not like at random. Of course, we want also to have the ability to scan through the entire set of k-mers in our dictionary. So that's iteration. There are also navigational queries. I mean, there are many types of queries that are supported, but again, I'll not talk about them for simplicity. So that's our problem, okay? So it feels like a fundamental problem, very, easy statement. So let's see what we can do. So to begin with, a quick remark, because maybe someone may ask this. So do we really need a specific solution to this problem? Actually, I asked myself, right? And so a few years ago when I started working on these topics, because I knew that the algorithmic literature is actually very rich of solution for the compressed string dictionary problem. In fact, you can refer to this survey paper by Martinez Prieto, also Gonzalo Navarro is there. And so they surveyed many solutions using front coding, many types of tries. My point is that, of course, you can use any of such solutions. They will work, of course, because they hold for generic strings. So they will also work for k-mer sets. But this is the point, right? You're going to incur in a big penalty in performance, both in space and time, because those dictionaries are relevant for variable length strings. They usually are, they assume that the strings are drawn from larger alphabet. So, for example, ASCII or Unicode, while, we are in a very specific setting because we have k-mers, so they share k-1 symbol overlaps. And of course, we want to exploit, okay, this fact that there is a lot of redundancy, okay, in the set. They are of fixed length. The alphabet is small. So as you can see, we have many, constraints in our problem. So this question is actually a little bit rhetorical, okay? So the answer is yes, we do need, okay, a specific solution. And indeed, the first tool we're gonna now introduce is, well, actually are a family of methods that try to keep k-mers as much as possible in a contiguous form, as much as glued as possible, exactly in order to avoid these k-1 symbol overlaps, okay? Because of course, if I store each k-mer, independently of one another, I will spend, let's say, 2k bits, okay, assuming that each character, each DNA base can be coded into 2 bits. So I'll be spending 2k bits, okay? But this is very wasteful, right? Because if I take this k-mer and this k-mer here, I will be repeating k-1 symbols, okay? So of course, we do not want to do this, okay? We want a space-efficient solution. So the first tool we're gonna see are methods that try to glue, okay, as much as possible these k-mers. And these are the spectrum preserving string sets. So to start with, let me first, establish this equivalence once and for all between a k-mer set and a de Bruijn graph. I'm pretty sure you have already heard about the Bruijn graphs, but I will try not to be boring. So here you have the formal, boring definition, but you can easily see from the picture what the Bruijn graph is. So it's a graph where each node corresponds to a k-mer in our input set. And we have a directed edge from, let's say, k-mer U to k-mer V if U and V share a k-1 symbol overlap, okay? Namely, the k-1 long suffix of U is equal to the k-1 long prefix of V, okay? So in this case, TCA has an incoming edge into CAT because, as you can see, they share CA, okay, these two bases. So this is an example for k equal 3, okay? So very, very easy. So this is a de Bruijn graph. So actually, we can talk about de Bruijn graphs and k-mer sets, and those are the same, okay? It's very easy. So let's see now what we can do to try to, reduce the redundancy in this graph. Because again, of course, note that, we're replicating a lot of symbols, okay? So all the overlaps here are redundant. So I guess everybody can immediately, say that, well, we can, of course, glue together all the k-mers along non-branching paths in the graph, okay? So if you're familiar, for example, with tries, this is exactly what we do from a trie to a compacted trie, okay? So we collapse all the strings together. So we collapse all the node by gluing all the characters stored in the nodes into a string. And here we are doing exactly the same. So from the de Bruijn graph, we obtain the compacted de Bruijn graph, where, as you can see, these strings are the glue, let's say, of all these k-mers, okay? So these strings stored, again, in the nodes of this compacted de Bruijn graph are known as unitics, okay? So for sure you've heard about this name, unitics. So why stopping here? We can do even better. We can reduce even more the redundancy because now we can also path cover this graph. So we can compute a path cover, and intuitively we do not just want any path cover, but we would like to have a minimum size path cover, okay? Something that has the least number of paths in the cover. And of course, this is trivial to do in this example. Okay, so we so this is in panel C, a minimum size path cover. And this allows us to also remove, okay, these two symbols overlaps, okay, between this unitic and this one, and this two symbol overlap between this one and this one. Okay, so we, save more and more characters. So, so these, glued unitics are sometimes called stitched unitics. And this is our first example of spectrum preserving string set. Okay. So what does it mean? So spectrum preserving string set, very intuitively, it means that, as you can see, it is a set of strings. Okay. So the last two words are explained. So a set of strings whose spectrum is equal to the de Broglie graph. So the spectrum is nothing but the set of k-mers, okay, of a given string. So formally, a spectrum preserving string set, or SPSS for short, for my sequence S is a set of strings that I'll call U, is a set of strings, such that if I take the union of the spectrum of all such strings, I obtain the original spectrum of S. Okay. And usually we also have this constraint. We have this property that if I take, the pairwise intersections of the spectrum, the intersection is empty, okay? For any I and j, of course. So this means that a given k-mer appears only once, okay, in one of my strings, in my SPSS. And this is a very nice property to have, right, for our dictionary of k-mers, because if we store the SPSS, I know that any k-mer to my original set, if present, is present in just one string. So I have to understand which string I have to look it up. All right, so for example, the set of unitics of the compacted de Broglie graph or the stitched unitics we just saw are possible SPSS for S, which also have this property here, okay? It's very easy to see. So in general, so what's our goal? In general, the goal is that we want to minimize, okay, the cumulative length of U. So this is a nice optimization problem. So we want to minimize the cumulative length, which means we want to minimize the number of characters, okay, of the strings in U. So we search for not just any SPSS, but we look for an SPSS which has longer and longer strings, okay? So the longer the strings, the better, because it means that, we avoid overlaps for our k-mers. So several solutions were proposed in the literature, and essentially all of them follow this general framework that I have described with just 2 sentences. They first compute the compacted de Broglie graph, okay? And then they compute a minimum size path cover, as we said before, okay? So all approaches are variations or incarnations of this general framework. And of course, depending on what exactly you do, but you obtain different SPSS with slightly different properties. And again, one nice property to impose is that the cover is disjoint node, which means that you're not allowed to revisit one node more than once. And if you do this, so if your path cover is also disjoint node, you have this property that each k-mer appears only once, okay, which is something that we really would like to have in order to, avoid redundancy as much as possible. So again, so these are, to the best of my knowledge, all the available SPSS that were proposed in the literature. So, starting with the unitics that are, I would say, a folklore method. Then in 2020, we had this couple of papers that more or less, proposed the same thing. Stitch unitigs or simplitigs are more or less the same. They were proposed independently by two groups. And they're also almost optimal. Paul Medvedev, in his paper, proved that stitch unitigs are very, very close to the lower bound. Oh, well, I mean, he established the lower bound, and experimentally, he and Raman showed that stitch unitigs came very, very close to the lower bound in number of characters. So they are, essentially optimal. But the question whether one can actually find a truly optimal solution remained open for a couple of years until Smith and Jarno-Lanko solved this problem in 22-23, and they showed that yes, we can actually output an optimal SPSS with the smallest number of characters. Although, again, the gap between this optimal and this almost optimal is tiny, okay? It's very, very small. So you can actually be very, very happy with just the stitch unitig heuristic, and it works very, very well. Then there are other types of SPSS, like the matchsticks and the masked superstrings that have, as I mentioned before, slightly different properties. In particular, they allow for repetition of k-mers. Yeah, that's more or less the general picture, the bigger picture. So I want to conclude this part about spectrum preserving string set with this remark. Okay, so we have, I mean, my final message is that we have very, very efficient algorithms that also have been implemented and tested. So something, very, very practical that can produce and process the following pipeline. So from an input very long sequence, they build the compacted de Bruijn graph in external memory using parallelism. So they are very, very fast and efficient. And from the compacted de Bruijn graph, they compute this path covering in linear time or almost linear time, like linear, n log n time, but this is still, fast. And finally, they output this collection of strings, okay? This SPSS with no duplicate k-mers. And these algorithms include BCOM2, Tupaco, the Cuttlefish papers, and ggcat is also very, very fast, is written in Rust. So I'm going to assume from now on that the input for our problem is this spectrum preserving string set. Okay, so a collection of strings with k-mers, very, very, much glued all together so that we have reduced a lot of redundancy. So now that we have our input SPSS, now the question still remains, right? So how do we now index this collection of strings so that lookup is efficient? Well, some people would say, well, we can compute a full text index for my collection of strings, like a BWT-based solution, like the FEM index, R index, the move data structure. I would say yes, go ahead. It's perfectly possible. I guess also Simon Puglisi will talk about the spectral BWT, which is also another option here. But my point is that BWT indices here are strictly more powerful because they, as you know, they allow for substring search. Okay, so they do not just look for k-mers, but can actually search for any substring. So for any length. So what we're going to see next is a solution specialized for k-mers and based on hashing. So a completely different paradigm than the BWT. So to do so, we need two more tools. And the next tool is minimizers. So So it's a point, this has an independent interest, but then we'll see how, of course, we can, use SPSS, minimizers, and hashing all together. All right, so again, consider our collection of k-mers, for example, here on the right. What we want to do is to look at each k-mer, x, and select some substring, some mmr for a given parameter m less than k, and consider this mmr as the representative of the k-mer. Okay, something like I extract this mmr and I say that this mmr, synthesize all the information in my k-mer. So it's a representative of the k-mer. And this representative goes under the name minimizer. Okay, so the minimizer is a specific mmr inside my k-mer. So here on the right of the slide, you have this example. Okay, so in pink, I marked all the minimizers of my k-mers that I've chosen using some logic. Okay, we'll see soon what is the logic. Of course, you would immediately say, okay, but why is this useful? This is useful because if I now look at the distinct minimizers that I compute, if I compute them in a certain way, we have this property that consecutive k-mers have exactly the same minimizer. Okay. So they tend to share the same minimizer. So if I look at the distinct minimizers only, this set of distinct minimizers is small, okay, compared to the total number of k-mers. So in this example, how many k-mers I have? 3, 4, I have 8 k-mers, okay? Of course, I have many, many more, but in this picture, I have 8 k-mers. And as you can see, the number of distinct minimizers is just 4. Okay, it's just 4 because, as you can see here, we have that for this last 4 k-mers, the minimizer is exactly the same. Okay, so the idea is that if I take this set of minimizers, if this set is small, this set of minimizers form like a succinct sketch for my sequence S. And of course, that working with sketches is a lot more space efficient, more, it can reduce the computational time of your downstream applications and so on and so forth. Okay, so we want these minimizers to. We want the set of distant minimizers to be small. Which brings us to the following question. So now, how do we compare different sampling algorithms? So different choices for the minimizer. So we need a performance metric. Okay, we need a metric to say, okay, look, this scheme is better than this other scheme. And from my example, I guess it's pretty clear that, of course, the better I would like to have the scheme which select as distinct minimizers, as fewer distinct minimizers as possible. Okay, so I define the density of a sampling scheme as the fraction between the distinct minimizers selected out of the total number of mmers that I have in my sequence. So if this ratio is small, then my scheme is good. Okay, so of course, the lower the density, the better my my sampling algorithm. So we seek for a minimizer algorithm with low density. The first thing immediately to do is to establish a lower bound for the density, and this is a very straightforward lower bound, 1 over W, where W is this quantity. This quantity, as you can see, is the number of mmers that I have inside each k-mer. It's very easy to see because as you can see, so this is like the best situation that I can have, okay? The best situation because the same minimizer repeats for its maximum number of times, okay? So this particular hammer cannot repeat for more than k minus m plus 1 times, because the next kmer, let's say, coming to the right of the last one, so A, C, C, G, A, T, T, C, A, and then something more here to the right, will not contain, okay, will not have this substring, okay? So this hammer, leaves, let's say, this window of consecutive kmers. And so the best I can do is to pick, okay, this hammer, which repeats for at most, W consecutive kmers, okay? So the best I can do is to sample one hammer out of W. So that's the best I can do. So the trivial lower bound to the density is 1 over W. I hope this is clear. So I can sample trivially, this guy. If this guy repeats for W times, that's optimal. But I cannot sample this for one extra time because this hammer will leave, okay, will not belong to my kmer. So the minimizer must for sure change, okay? So this established this lower bound of 1 over W. Okay, so let's finally see what's a simple, logic to select an hammer as the minimizer. Well, perhaps the simplest thing to do is to fix an order over the hammer. For example, you would immediately say, well, let's look at the lexicographic order because it's very easy to see. In this case, I take fixed an order, the hammer that is the smallest with respect to that order. So in this case, for this particular kmer, this is the set of all its hammer, and it happens that this one, AACC, is the smallest one. So according to lexicographic order, so I say, okay, this one is the minimizer for my kmer. So usually in practice, we do not really use the lexicographic order because this has some problem with repetitive regions in DNA. So we actually randomized these algorithms, and we use a pseudorandom hash function H, okay, and we choose the hammer as minimizer that has the smallest hash code. Okay, so now, as you can see, the order O is defined by this random hash function. Okay, so we randomized the order. So in this case, as you can see, it is no more AACC, but in this case is GGTA because it happens to have this smallest hash code. So if we do this, again, we obtain a family of randomized algorithms, and there is a simple randomized argument that shows that the density of the random minimizer is this value, this quantity. Is 2 divided W plus 1, where W, I recall you, is K minus M plus 1. Okay? So compared to the lower bound, which is 1 over W, as you can see, this is roughly a factor of 2 away from the lower bound, which I would say, is unsatisfactory from a theoretical point of view, because of course we wonder whether we can get, close, right, to the true lower bound of 1 over W. But on the other hand, in practice, it's quite good. I mean, a factor of 2 away is not a big deal. So in practice, random minimizers are like everywhere. Okay, they are very straightforward to implement, very easy to analyze. So actually, they are used really everywhere in bioinformatics. So let's now consider this plot, this performance plot for the density. So as you can see, the red line, the flat red line is the random minimizer. Okay, it's flat because again, its density is 2 divided by W plus 1. Okay, so in this plot, I fix W to 24. Okay, it's just an example. And I keep varying M and K. Okay, so M and K grow, and W is fixed. Okay, so that's why, you know, the random minimizer has a flat line. Okay, so it's 2 divided by W plus 1, so it's gonna be 2 divided by 25, which is 0.08. Okay, so more or less here. The minimizer was proposed in 2003, 2004. Then later on, some development was made. So we had this miniception approach, which, as you can see, obtains a lower density for some practical values of M. But then, you know, again, it loses out to the random minimizer. Okay, so then, you know, if you keep increasing M, it doesn't work anymore. And it's also conceptually not that easy to understand. So if you look at the papers, I mean, they are excellent papers, amazing results, but the math that they do, the argument that they use are quite involved. And especially for the double decycling minimizer, so this green line, as you can see, it improves a lot. It came also, you know, it comes also close to the lower bound, but it's not very intuitive. I mean, why, you know, it has this particular behavior. And so, you know, starting to look at those pictures, I asked myself like a couple of years ago whether there was something fundamentally better than the random minimizer. And by fundamentally better, I mean not only better in terms of density, of course, but also better in the sense that is as easy to implement, as easy to understand, as easy to analyze than the random minimizer, and also has better density. So this remained an open question for quite some time, and then finally we, you know, so to speak, we solved this by proposing the mod minimizer, me and Ragnar Groth-Korkamp last year. That, as you can see, has this blue line. Okay, so its density, we can prove that its density, you know, reaches the optimal value in the limit when we increase K. So we keep improving, and, you know, coming very close to the optimal density. So the optimal density, I mean, close to the lower bound, of course. And actually, along, you know, in coincidence of these peaks, the mod minimizer, sorry, is optimal. So and it has a very simple proof of the density. It has a nice closed form formula, so it's easy. So it's really as easy, well, a little bit more involved, but more or less as easy as the random minimizer. But it achieves a remarkably better density for long K. Okay, for relatively long K and long M. We improved also more on this result this year. I mean, at the beginning of this year, where we proposed the open-closed mod minimizer, which is, I would say, like a combination of the mod minimizer with open-closed sync MERS, something that I, you know, don't have time to explain. But you can see now that we really are, you know, catching up, let's say, with the lower bound. And but now I mean the analysis is a lot more complicated. We don't have a closed form formula, so, you know, there are still many open problems in this area. And we also conjectured that there is no scheme that can really go exactly like the lower bound, but we conjecture that there must be like a smooth interpolation between these points, like this one and this one and this one and this one. Okay, so there must be like a smooth interpolation which is exactly what the purple line is doing. So we conjecture that this could be optimal, but a formal proof is still lacking. So maybe we can also make the lower bound tighter. Maybe we can raise the lower bound. Who knows? So those are still open problems. Still, I mean, if you want to plug and play with minimizers, have coded this library, and you can run all these algorithms and see how they work on your data. Okay. Sure. Yeah.
I think with Apple giving picture several perspective of this results. And my question is, what types of application is a long M, especially for
that's
28 and longer?
That's a good question, actually, because so for the dictionary, we're going to see typically M is between 20, 25, true, but no more than that. So actually, you're absolutely right to ask this. To my knowledge, no application needs like a very, very long M, and nor even a very, very long K. So we don't really know whether in the future we'll use a very long K, like I don't know, 500 or 1000. So usually K is in between 31, 63. So yeah, so your question makes sense. So actually, this is like I would say theoretical analysis, but in practice we use values, let's say in this range only.
Oh.
Yeah, true. Absolutely true. In fact, this is also another open problem. The other open problem is who cares about the, let's say, the behavior in the long tail, like in the long regime when M and K are very long. How about this particular regime? Okay, can we make minimizers like optimal, so exactly equal to the lower bound? This is still an open question. Yeah. All right. So last two very briefly, because this is it would require like an entire talk by its own. So we'll be very quick on this. Minimal perfect hashing. So at least you get the definition, and you can then study by your own. Yeah, so a minimal perfect hash function f for a set of n distant keys is something that map bijectively these keys onto the range 1n. So you have an example here. You have your favorite collection of strings. So Tokyo, Shinjuku, ramen. So they must be all, of course, distinct. Otherwise, the problem doesn't make sense. And you want to build this function, which is a data structure, actually, that maps all of those keys into a unique identifier, okay, between 1 and n. And you know why this is called minimal, because as you can see, there are no holes, okay, in this logical table. And it's also perfect because there are no collisions, okay? Oh, we have a question?
No.
No, okay. And there are also no collisions, okay? So each key gets its own slot, and that's it. Again, a minimal perfect hashing is a very old problem. People started to work on this like in the 60s. Then of course we didn't produce any results for many years. Then at some point somebody proved something. In particular, here I've put the main milestones, or the main properties of all these functions that we can build nowadays. So the first milestone was achieved by Melhorn in 1982. So he proved that any minimal perfect hash function must use at least that amount of bits per key. So as you can see, these functions can be built in a very compact way. So they, they are very, very space efficient. And we have like a huge variety of approaches to build such functions. And I will show soon a picture. And these are their most important performance characteristics. So they are very fast to evaluate. So once you have built the function, if you want to compute, for example, the identifier for the string sushi, which is 4, okay, in this example, now f of sushi can be computed in a few nanoseconds. Okay, so it's very, very super efficient. They're also very fast to build from your collection of strings. So most of them have expected linear time construction. And again, they're also very space efficient, okay? There are some approaches that came close to this lower bound, but most approaches stay in between 2 or 3 bits. If you are then interested in learning more about this algorithm, we have a survey, really recent, like about published on Archive like 1 month ago. And this is collaboration with, as you can see, many excellent people in the community. Peter Sanders, Sebastian Oviña, Stefan Balzer, and others. And I just want to, show this. So this is, actually, these are not even all the approaches. So these are all the practical approaches. There are also others that are more theoretical. So as you can see, we have a really large family of different approaches. So we divided them into 3 main categories: retrieval, brute force, and fingerprinting, according to what they do. But as you can see, there are some approaches, for example, this one or this one, that actually, as you can see, combined different paradigms from different, categories. So yeah, so just to say that this is a very rich, let's say, problem with many solutions, and all of those solutions are actually also very well engineered. So it's not just a matter of, let's say, making the formal analysis, but they can actually be coded, like written in software, and they're very, very efficient. In particular, I want to point out that in 2021, we proposed this approach called PT hash, which stands for pilot table hashing. That has this focus on especially fast lookup time, because in my opinion, and I'm still very much convinced, the most important aspect for minimal perfect hashing is lookup time. So your function must be very, very fast to query. That is because usually we build such static data structures once, or at least, let's say, every now and then after your data structure has been built, then you query, okay, most of the time. So it's actually the, most of the time is spent in querying the data structure, not actually for building and so on. Of course, building time must be efficient. Of course, space must be good, but it's lookup time that is the most important aspect. And so, starting from our paper in 2021, many people got involved, got interested in this approach and started to produce many variations. In particular, the German people working with Peter Sanders went on fire on this PT hash family, and they, produced many variations and many optimizations. So also Ragnar Groot Korkamp wrote his own version of PT hash in Rust, so PTR PT hash Rust, and which is also very fast and very space efficient. So again, if you want to super fast perfect hash function, just click here and you find all the references. Okay, so that's all about minimal perfect hashing. So just the bare scratch. So now in I would say 15 minutes we'll conclude and put together all the tools we've seen into our final dictionary data structure. So stay with me a little bit more. So let's start conceptually by recalling what we just saw. So we said that consecutive k-mers tends to share the same minimizer. So I can define a super k-mer as a maximal sequence of k-mers that share the same minimizer. So in this example here, as you can see, this substring is a super k-mer. It's a super k-mer because if I take all its constituent k-mers, all of them have exactly the same minimizer, which happens to be AACC. Okay, so here I'm using lexicographic minimizers just for examples. Now, if I take this other k-mer, then now the minimizer changes. Okay, so also the super k-mer changes. So this guy here highlighted in blue is not part of the same super k-mer. So note that any k-mer in my dictionary, in my SPSS, must be part of some super k-mer. Okay, so what I have to do is to compute its minimizer, locate the super k-mer in my input string, and I know that my k-mer, if present, must be part of that super k-mer. Okay, that's idea. So what I have to do is to locate those super k-mers in my input spectrum preserving string set. Okay, and to do that, we use a minimal perfect hash function. Okay, so now you have all the pieces of the puzzle, together. So SPSS. So inside the SPSS, we locate the super k-mers that are, again, maximal sequences of k-mers sharing the same minimizer. And we index, okay, those super k-mers using a minimal perfect hash function. So what does it mean that we use a minimal perfect hash function? It means that we take the set of all the distinct minimizers and we build a minimal perfect hash function for this set of minimizers. Okay. Now, if I query a minimizer using my minimal perfect hash function, let's say I query the minimizer mu, okay, so this string in this example, of course, the minimal perfect hash function, as we said before, computes a unique ID between 1 and the total number of minimizers that I have in my collection. So let's say I, okay, this ID I. Then I can use this I as an index in a table, and I store at that position the offset, okay, of the super k-mer that has this minimizer. So that's how I allocate the super k-mers in my input SPSS. So in this example, at the entry given by the minimal perfect hash function for this minimizer, I store this position, so the position of the first nucleotide in the corresponding super k-mer, and I also store this other position, okay? Because as you can see, this minimizer happens to appear twice. This is possible, of course, okay? So if the minimizer appear multiple times, then I do not only have one single offset to store, but I have more than one offset to store. The idea, nonetheless, is that since we are building the minimal perfect hash function for the set of minimizers, not for the entire set of k-mers, this index is sparse. Okay, so it waits, so it's very compact, so it doesn't waste a lot of space. So it's sparse because the space of the index is directly proportional to the number of minimizers, right? And so using random minimizers, we have that we got, for example, for K31 and M equal 20, we got something like this. We got 6.5 times, so if I apply this number here, so we got 6.5 times less minimizers than k-mers, okay? Which is a good sparsification factor. So upon lookup, what I have to do is, again, we compute for our k-mer x its minimizer. So here it is. Then we evaluate the minimal perfect hash function. This function will point us to a position inside an array. And at that position, I recover the offsets. Then I jump in my SPSS at those offsets, and then I look for my k-mer. So I know that if my k-mer is part of my SPSS, then it must be found in one of those two super k-mers. So either it's found here, if not found here, it must be found here. If it's not found even there, then my k-mer does not appear, okay, in my input collection. That's the idea of sparse hashing. So very easy conceptually, and it works very, very well. So here is another example. So as you can see, we have 4 strings, like a blue, green, yellow, and red in my input SPSS. For some parameters, k equals 31. I mean, it's not really important. And here on the right, I'm showing the complete set of minimizers for m equal 8. And on the right here, we have all their offsets. Okay, so pointers inside this spectrum preserving string set. Of course, the very important point is that we do not store those strings for the minimizers. Okay, so remember, a minimal perfect hash function doesn't store the keys. Okay, it's just a map from a key to an identifier. That's it. Okay, so I'm showing them just for visualization, but we do not store such keys. So in practice, we store the SPSS, of course. We store the offsets and the minimal perfect hash function. That's it. So this is the overall schematic data structure. So again, very briefly, we have this minimal perfect hash function f. We have the SPSS, as we said. We have the offsets. And then also we have some auxiliary, very small, sequences like the sizes, which means that I have to understand how many offsets a minimizer can have, because it can also appear multiple times. So I have to store this information, but those are small auxiliary sequences that do not weigh that much. And so in this picture, we also have the flow of query for this particular k-mer. Again, we compute its minimizer, so this highlighted sequence in bold. We look for the minimizer in the minimal perfect hash function. This function gives us identifier 7. It gives us identifier 5. So we look at position 5 in this sizes array, which point us here. And so these are the 2 offsets that I have to consider. So which means I have to jump at position 9. And if I do not find my k-mer here, I jump at position 255. And I look for my k-mer there. In this particular example, I find my k-mer x in this second super k-mer here at this blue position. Okay, so this is my k-mer that I found. Okay, this is the k-mer x. So now we get to the most important property of this data structure. So it should be intuitive that if I look for the k-mer coming immediately after x, say for, the k-mer that has exactly all the k-1 symbol overlaps, and then here it has another nucleotide. If this is present, it must be found exactly here, okay? It must be found exactly where I was, shifted by one position to the right. Okay, there's no other option. So if I called, for example, I, the result of the lookup operation for x, then its successor will have result I plus 1. Okay, so this is a very important property because it means that the order of the k-mers in the input SPSS is preserved. Okay, so this data structure, because it stores, okay, the SPSS and plus, of course, the mechanism to search this SPSS, is able to preserving the order in the input SPSS. And this is very, very important. This is important because if we keep k-mers in order, like in the original order, we induce a natural clustering for the satellite data that we typically want to associate to k-mers. Namely, sometimes we want to store the abundance count of k-mers, or we want to store the color set of k-mers, and we will see this application on July 4th. And if we, if we have this property that k-mers are kept like in order, you can immediately understand that, it's very intuitive to see that each time you see a k-mer X, chances are that you also see its successor, in this case, W, okay? Why? Because X and Y, being one the successor or predecessor of the other, are more or less the same, right? Are more or less the same strings, so they overlap by k-1 symbols, and they just, differ for one base. So every time you see X, chances are you also see W. So all its abundance count, color sets, all the satellite data that we may want to store will be almost the same. I mean, if not exactly the same, they will be almost the same. And so this order preserving property given by lookup has this nice effect that is giving us some clustering of the satellite data. So we cluster all the abundances, we cluster all the color sets, and of course, every time you have clustered data and sorted data, people doing data compressions are very, very happy, right? So they smile, they tend to smile a lot, because if you have clusters of equal values, like rounds of equal values, they can be compressed very well, right? So again, and in fact, we're going to see, a killer application of this property on July 4th, okay? So yeah, so that is really the most important message of this talk. It took me a while to get here, but this is the most important message. Well, there is also formally this other component of the index, the skew part, that solves this problem. I'll be very quick. The problem is that sometimes some minimizers is very repetitive. For example, on the human genome, for these parameters, there could be some minimizers that appear this amount of times. Okay, so many, many times. And this is a problem with the structure we have just explained, because in the worst case, it means that we would have to, scan, like inspect all of those super k-mers, which is, of course, a nightmare. Okay, so the lookup time will be terribly slow. But here is a property that we can exploit. Such minimizers are very, very rare. Okay, they almost never happens. They do happen. Okay, so there is some guy being very repetitive, but actually, if we look at the fraction of minimizers that appear, for example, twice, 3 times, 4 times, and so on. As you can see, these are just, for example, 0.4%, 0.2%, okay? So most of them, as you can see, appears for 97 times just once. Sorry, for 97% of all the minimizers appear just once, okay? For a reasonably long M. So we can exploit this property to actually build another minimal perfect hash function for all the k-mers that belong to super k-mers that appear many, many times. That's the idea. So so this is formally what we do, but again, it's not important to go through this thing. Maybe I can directly comment on this example. So this example shows an example of skew hashing. So if I query for this minimizer, I detect that it appears many, many times. Okay, these are all offsets in the string of all its super k-mers. So potentially, what I have to do to find this minimizer X is to look into all of those. In the worst case, I mean, of course, I can be lucky and find this X immediately in the first super k-mer, of course. But in the worst case, I would have to go, all the way down and scan all of them. Okay, so this is too much, okay? As computer scientists, we want something fast. So if I detect that my minimizer appears many times, more than 2 to the L times in this example, then I know that I can look it up into a different data structure, which is another minimal perfect hash function, which gives me directly the ID of the super k-mer that I have to scan. That's it. So I can jump directly to the super k-mer ID 8 and just look my k-mer X inside this super k-mer. And that's it. Okay, so I don't have to scan through the entire things. And again, the idea is that this skew hashing component, again, it's a very small part of the data structure, because such minimizers that are very, very repetitive are just very, very few. Okay, so I just have to handle those nasty guys, and I'm done. Okay, so and I can spend very little space to handle those. All right, so I'm basically done. So thank you for the patience. So I just want to conclude to say that, of course, I've implemented everything in this tool called SSHash, which stands for sparse and skew hashing of k-mers. It has been very useful in many applications, and so many people use this index to build other tools. So I'm very happy, because it means that the library has been tested quite a lot, so it should be very robust. And amazingly, we keep improving. So recently I improved some parts of the library. In particular, I improved a lot the construction time and also streaming queries. So these are extremely new benchmarks that you can also find online at the GitHub repository. Of course, as you can imagine, in the original papers, I compared SSH to the state of the art, of course. So to what it was the state of the art back then in 2022. So there were solutions based on the BWT, of course, others based on the hashing, and since I published the paper, of course, SSH was a lot faster and more space efficient. But from the year 2023, I guess, other solutions were proposed that are trying to, you know, challenge SSH. Some of them are a little bit, you know, smaller, but slower. So you know, soon I would like to also grab all those new approaches and reevaluate everything into comprehensive benchmarks. These are just, you know, example numbers. So as you can see, we can build SSH for the whole human genome in a bunch of minutes. So it's very, very fast. We can query for streaming lookup in, you know, in 100, maybe 200 nanoseconds per kmer. And if we also increase K, as you can see, the space usage goes down. And this is a nice effect of using minimizers. Okay, so if we increase K, then super kmers, you know, become longer and longer. Minimizers are sparser and sparser. And so the data structure becomes to be more and more space efficient, which is also something that is not possible, for example, with BWT-based indexes. Okay, so if you increase K, the space doesn't change that much. Instead, for SSH, if you increase K, you get down and you keep going down. All right, so I'm done. To sum up, in this long talk, we saw this solution to the K-mer dictionary problem, this order preserving, and along the way, we, you know, defined, we actually barely scratched the surface of these three tools: spectrum preserving string sets, minimizers, and minimal perfect hashing. And then we combined all the three into this solution based on, again, sparse and skew hashing. Code is available. There are many extensions that were proposed through the years, starting from 2022. Namely, I've shown how to leverage the order preserving property to compress very well the abundances. We can support our other types of queries. So all of this I, you know, made in collaboration with some fantastic people from both University of Helsinki and people from US. And again, on July 4th, we'll see, you know, this topic, which directly build on top of SSH. All right, I probably took a lot of extra time. Yes. Thank you very much for your attention. And if you have any questions, thank you. Thank you.
Okay, question. The last payment, the last application did you support for this?
So in this case, I'm just benchmarking the dictionary itself. So I'm just looking at how fast the random lookup time is, how fast we can stream through kmers. So for example, for colored compacted de Bruijn graphs, we need this streaming lookup performance. So yeah, so this is not, you know, for some particular application in mind. It's just the performance of the dictionary itself. So of course, if the dictionary is efficient, then, you know, all the applications on top are going to be, you know, reasonably efficient. Yeah.
Okay. And in stream processing, given compression works with a property of highly efficient, like it's learning speed also uses property and grammar compression. Exact type compression uses same property of highly effectiveness.
Yeah.
And this talk doesn't, in my understanding, this talk will not use such property. Is there any research direction for using methods evaluating?
Yeah. So I see what you mean. So So the thing is, so what you're saying is that this collection of strings is stored like in plain form. So we do not use like BWT to actually compress. Yeah, so that's true. That's also why, for example, if you use the BWT to solve this problem, you get smaller space. But my point is that you also destroy the order of the k-mers. So you lose this property that you can actually look up for consecutive k-mers in a very cache efficient manner. So of course you have a space-time trade-off. So you could use any BWT or LZ based methods here, but you will incur in a big performance penalty for query time, and especially if you want to build tools on top of this, you really want this order preserving property, because for example, when we will talk about colored the Brownian graph in a few days, we'll see that for each unitic we want to associate a color set, which is a list of integers, let's say. And there are some tools that, based on the BWT, who spend a lot of space because they need to now compute the permutation of unitics into the color sets. And so you see, on the one hand, you save space by using the BWT, but then when you want to associate extra information, you need now extra space. So, you achieve more or less some balance, while, for example, in this case, you don't need any extra space. You can direct exploit the disorder preserving property, and you don't need any extra space. So, yeah. Yeah, exactly. So the things try to tends to balance, no? So all the gain coming from the BWT, now it could be lost if you want to associate information on the k-mer basis or unitic basis. Then you need more space to actually map unitics to this extra information. So yeah. Thank you very much.